Hello everybody, as promised I'm making a video for the titration problem that we couldn't go over in recitation today. But first I want to go over just kind of the pattern of titration. So we're always going to have these two different cases. We're either going to be titrating a weak acid with a strong base, or we'll be titrating a weak base with a strong acid. And essentially I want you guys to realize that there's a pattern at every single point of the titration. When initially we will ask you for the pH initial conditions. Somewhere before the equivalence point, we'll ask you probably at the equivalence point and then some point after the equivalence point. So initially, we know how to do that, right? Because it's just really finding weak acid equilibrium. So we're just going to use a Rice table, and we're not adding any titrant yet. But then once we start to add a titrant, then we're adding something strong to something weak. So we're going to need to use a BCA table to determine how many moles are changing. And then because we're at this before equivalence point, we still have some of our weak acid and our weak base. So we can either use a Rice table or a Henderson-Hasselbalch equation. So the important part here that's also kind of fun is that we have the half equivalence point, where the number of moles of our weak acid equal the number of moles of our weak base. And this is helpful for us because at this point, the pH equals the pKa using the Henderson-Hasselbalch equation. So that's kind of like a nifty trick that kind of can help you find the pH quickly. What's important is that before we've reached the equivalence point, we have our weak acid and our weak base. But once we reach the equivalence point, what that means is that we've added just enough of our strong base to react all of our weak acid analyte. So at that point, all I now have will be the conjugate weak base and the strong base, because I'm adding even more of the strong base past the point that it's even going to be reacting with the weak acid. So at this equivalence point, the weak acid equals the amount of weak base that I have. And to find the pH at the equivalence point and after, we have to use the BCA table and our Rice table. But the important thing to realize here, and I've written it down here, is that when we're using our Rice table, we can use our Ka here because we still have our weak acid forming equilibrium with water in our Rice table. However, at this equivalence point and onward, we no longer have that weak acid. We only have a weak base. So I'm going to end up using a Kb when I use my Rice table because I have a weak base forming its equilibrium with water. Now the same thing is going to be true over here. It's just kind of flipped. I have a weak base being titrated with a strong acid. So when I'm asked to find the pH initially, again, it's just a Rice table looking at the equilibrium that a weak base has with water. But then I start adding titrant. And then I'm going to have to use a BCA table and then a Rice or Henderson-Hasselbalch equation in order to find the pH. So the same thing at our half equivalence point, we have equal numbers of our weak base and our weak acid, and both are present. However, once we reach that equivalence point and onward, I no longer have the weak base I was titrating. I only have its conjugate weak acid and the strong acid that I keep adding into the reaction vessel. And so before the equivalence point, use your BCA and Rice table. After the equivalence point, you're still using BCA and Rice table. What's changed is that you no longer have this weak base. You now only have its conjugate weak acid. So you change your reaction from being your weak base in equilibrium using a Kb to after the equivalence point looking at the weak acid conjugate and its equilibrium with water using a Ka. Okay, so that's kind of the lowdown on this. I think that these little drawings right here are really helpful in summarizing the information about titrations. Now what I'm going to do is take you guys over here. This is a program that I made in order to help myself be able to answer any titration problem you guys ever ask me about. I can just kind of cheat and plug in these values and find the pH. So the example that I'm doing right now is trimethylamine. So that's going to be a weak base because you're thinking amine, that's a nitrogen. So the lone pair on that nitrogen is going to act as a Lewis base to steal the hydrogen off of water. Okay, so I'm doing a weak base with a strong acid titration. And let's just say we're using HCl. So I've told you here that my titrant concentration of HCl is going to be 0.125. And that the volume that I needed to add, the analyte volume is 0.025 liters with a concentration of 0.1 molar of my analyte and that the Ka of that trimethylamine is 6.45 times 10 to the negative fifth. Okay, and I'm even going to tell you my equivalence point, which you could have found by yourself, but I went ahead and did it for you. So again, look, initially, here's the rice table that I set up. I have that weak base, the trimethylamine, with its equilibrium with water to form the conjugate acid and hydroxide. So when I solve for my rice table and I solve for X, what X represents to me is the total OH concentration. So in order to find the pH, I have to say 14 minus the pOH equals my pH. So I find that to be 11.39. Okay? Then before the equivalence point, I still have to set up a BCA table because I'm going to be adding this strong acid HCl. So here again, this program is pretty general. So in our case though, we have the trimethylamine HCl forming its conjugate acid and water. So I have to go into moles here. So I use the analyte volume and the analyte concentration in order to find the number of moles that I have. And then I'm going to change by a certain amount of that H+, and I'll react both of it. Okay? And then I have my total volume. And now I can go into my rice table, again, using molarity. So I have that moles divided by the total volume gets me into molarity, so I can use my rice table. Here, before my equivalence point, I still have my weak base, and I just have some of my weak acid as well. So that's why my reaction still looks like this, and I'm still using a Kb. Okay, so now I use my rice table, normal equilibrium stuff. I mean, you guys got this. I find the value of X. X represents to me OH concentration. So I find the pOH and easily can get into the pH. What I have here on the side as well is if you use the assumption, here I've calculated the pH to not use the assumption, but here we made an assumption. Look at how they're essentially the same, okay? Then at the equivalence point, I've added enough, again, in moles for my BCA table, I've added the same number of moles of my strong acid as I had of my weak base. So that means that I've reacted all of it. All of my weak base is now gone. I've used up all of my acid, and now I only have my conjugate weak acid left. So when I divide that by the total volume to go into my rice table, all I have for equilibrium is that weak acid. So that's what I use for my reaction for this rice table using a Ka. Okay, so you find the Ka by using the Ka times Kb equals Kw formula to get that Ka. Then I set up just a normal rice table. I solve for X. X relates to me the total H+ concentration now. Because I'm dealing with an acid, when I find equilibrium and I find the value of X, I'm now looking at how much H+ is being put into the solution. And I'm able to find that to be 5.53. So again, we can just take the negative log of X at this point because that's what X represents. I found that using my rice table. Now I'm at the after equivalence point, meaning I'm adding even more acid than I need in order to neutralize the base. So here's the number of moles of base that I have from the very beginning, and I'm adding a boatload more acid. So I'm only able to react this much of the acid. Okay, so I use up all of my base, but I still have some acid left over, and I'm forming as much of that weak acid that I can from that conjugate base, okay? So now when I go into my rice table, all I have in terms of my conjugates is that weak acid. So I divide the number of moles of my weak acid by the total volume to get the initial concentration of that weak acid. But I already have some H+ already present because I added so much in there. So I divide the number of moles of that acid left over by the total volume to get its concentration. So then I set up a rice table like how I'm used to, and I'm using a Ka because I'm starting with the conjugate weak acid. Then I solve for X. X, however, no longer is just the the H+ concentration. It's the amount that I have due to the dissociation of my weak acid, but I need to take into account the fact that I have some H+ already present. So you can see the formula in here. It's my value of x plus my initial amount. And it just so happens that x was just such a tiny, tiny number in relation to how much I had here. You can really see that the pH is completely dependent on how much of that strong acid I was adding in there, because I was adding so much more. And so the pH is going to be pretty low, 1.64. Okay, so that's how we're kind of going about these titrations. It really is the same pattern every time. The thing that I always look for when it comes to the before equivalence point is not always going to be the half equivalence point, but it often actually will be. And what you're looking for is that these two numbers need to be the same. When you see that, you're like, I'm at the half equivalence point, I know this, okay? And then at the equivalence point, you're always looking for this diagonal relationship right here, that you should have the same number of moles over here, and that relates to you, that you're like, okay, I know that I've done my at equivalence point calculations correctly. And after equivalence point, you're always looking for some leftover of your titrant, and then as much of your weak conjugate that you could have made. All right, so that's the same thing you're going to do, and I also have this related to us for a weak acid strong base titration. I'm not going to go over that because what we have here is essentially the same thing. So I feel confident that you guys probably feel pretty good about this. If you do have any questions, please let me know, or if anything in the video didn't really make sense. Remember to look at this right here. Really is super helpful in realizing what you need to do at each point. And you can really see that's actually like pretty simple. I know that this maybe doesn't look super simple, but look, you're just doing a BCA rice table. Oh look, you're doing a BCA and rice table. We're just realizing that you have to change the reactions. So I believe you guys are going to do awesome on this exam. The other really important thing that I want to say to you guys is that titrations are beefy and they're important, but it's not the only thing on the exam. Remember that we've covered our strong acid-base chemistry, so neutralizations. We've also done a lot with buffers, so you need to be able to do that. We've done solubility, KSPs. We've done complex ion formation using KF. So just like realize that titrations are a part of this exam, but it's not the only part. And you need to be able to, do it all. Use the necessary skills list in order to see everything that you need to be able to do. So titrations are important, but don't forget about everything else. Good luck over the long weekend. We'll have the exam examples in class on Monday. You guys should be really prepared.